Hi and good morning, and welcome to this webinar titled Critical Power Protection for Hospitals, Design Considerations for Selecting a UPS System for Healthcare Environments in accordance with HTM 0601 guidance, which is being held by Kohler Uninterruptible Power in association with the monthly IHE magazine, Health Estate Journal. My name is Jonathan Bailey and I'm the editor of HEJ. This CPD accredited webinar will cover the fundamentals of designing a UPS system, enabling healthcare engineers to explore the various UPS options available to suit their requirements. Kohler Uninterruptible Power says that, as with medical IT systems, there is no standard one-size-fits-all solution. Today, Alex Ems, the company's technical director, who will be presenting, says, as healthcare facilities and operating theatres rely heavily on technology for patient care, it's crucial to have reliable power protection solutions in place. This session will offer valuable insights into the latest guidance provided by HTM 0601 and cover an overview of risk to business continuity, fault clearance, transformer versus transformerless design, batteries, and selecting a UPS for medical IT. Also covered will be key UPS considerations, including understanding the load, supply requirements, redundancy, battery autonomy, redundancy and monitoring, as well as design for installation, access and maintenance. During the webinar, please type in any questions you may have for the speaker using the questions tab on the right of the screen. And at the close of his presentation, I'll put as many of the questions as time allows to Alex. I'm sure you'll find this an interesting and informative session. Alex, over to you.
Thank you, John, and hello to everyone who's joined. My name is Alex. I'm the technical director at Kohler, and like John, for the presentation, I will turn off my camera because you don't want to be looking at me the whole time. So, as John has mentioned, we've got quite a lot to cover. There's a lot to do. Just have a very brief overview of Kohler and KUP. And we look at the requirements for UPS in healthcare and looking at, the main parts of the UPS. We look at dual sources and isolation transformers, fault clearance, the requirements for batteries, and at the end we go through like a summary of what you need to consider selecting a UPS in the healthcare environment. And hopefully we'll be able to get to as many questions as possible. So Kohler is a large family-owned business from America, actually in a place called Kohler in Wisconsin. And they've got four main parts: kitchen and bath, decorative, hospitality, and energy. KUP is part of the energy group, along with their engines and generators businesses. We also do CHP of Clark Energy in Liverpool, and recently acquired Curtis and Healer to complement our portfolio. We look after sort of like microgrids and control systems as well. Kohler is sort of over 36,000 employees with over 50 production sites in 17 countries. Kohler Uninterruptible Power, KUP, was founded in 1997. We were the first company to bring in transformerless modular UPS into UK and Ireland, and acquired by Kohler in 2008, which allowed us to grow and expand and invest, opening an office in Singapore in 2010 and acquiring Pure Power Systems in Ireland in 2017. We renamed to Kohler Uninterruptible Power in 2019, and as part of the Kohler Group, 2020, 100 years in power, and this year 150 years in business. So we supply UPSs, emergency lighting systems, IPS, and of course the standby generators. Kohler generators are the third largest manufacturer in the world. But what is very key to us is our service and our excellence in service, best in class customer service. We have our own engineers to work on all UPSs. So applications now for secure power in all sorts of places. Obviously healthcare is what we're talking about today, but we're putting in UPSs in lots of different places, as you can see, from data centers through to government, defense, telecoms, and these being used for all sorts of mission critical applications now, because everybody needs everything to be on for 24/7. So healthcare has got a lot of requirements for UPS in particular, and these requirements are defined, or guidelines, from BS 7671, and there is section 710 on medical locations, and we have, of course, BS 7671 section 56, which is about safety services, and that has some sort of critical guidance. And of course, for healthcare, the HTM 0601, which gives a lot of guidance around a lot of things, and especially around UPSs. And it talks about the risk to be considered for business continuity due to loss of supply, and obviously risk to patients. Okay, so business continuity is from 4 to 1, from business support all the way to critical medical support services. And for the risk to patients, we go from E to A, so the support services, circulation, all the way up to the life support and surgery places. So the grade A is obviously the highest, and this is where we look to protect the supplies. So it does give in HTM a guideline of grading the risks, and we see it gives interruption times which are permissible from 0 to 0.5 seconds, 0.5 seconds to 15 seconds, and then 15 seconds to 3 hours. So we typically see UPSs being used for medical IT supplies in a risk grade A and B locations, with group 2 equipment requiring interruption of 0 to 0.5 seconds. Now, 0.5 seconds is actually a long time for obviously some computer equipments. So where we need that 0 interruption is where we're going to use the UPS. So we'll have a look at some of the UPS fundamentals as according to HTM, and they discuss double conversion UPSs, and these are known as VFI SS111, and we'll have a quick look at that in a minute. And it says it must comprise of a rectifier, an inverter, battery, static bypass, and maintenance bypass. Okay, and these are typically arranged in a lot of UPSs like this. So we have the rectifier with the mains coming in, AC to DC, then we convert the DC back to AC using the inverter. The battery is connected to the DC in the middle, and this is where we get dual conversion. And we have a static switch to transfer between online and offline, between inverter and bypass. And we have a maintenance bypass to be able to bypass everything is needed. Many double conversion UPSs can have a single or a dual input. Okay, and we'll talk about that quite a lot more. Now, there's also talk about a single conversion UPSs, okay, which are typically VI or VFD SS111. And what this means is we have a single supply feeding a charger rather than a rectifier, and then the battery. From the battery, we use the inverter to make AC, and then we have a static switch on the bypass. Now, typically, these are running on the bypass, feeding the load until the mains fails, when we take it from the battery and feed the load this way. Now, most single conversions UPSs don't typically have an internal manual bypass, and quite often they have only the option to supply from one source, and typically batteries are internal and for short autonomies. So they have their use in healthcare, but we see the differences. Now, there's a lot of discussion between transformer and transformerless design. Many modern transformer UPSs are transformer-less. There's a lot of advantages to transformerless, and the difference is, traditional UPS would have an output transformer that would step up the inverter. It was there because it was the only way to produce the required output volts because of the low DC bus. Modern transformerless UPSs have a high DC bus where we can make the output voltage without a transformer. Okay, majority of UPS manufacturers are supplying transformerless UPSs now, and we look at the requirements and the differences as we go through, so we understand. And we have different types of architecture with UPS. So we can have like a standalone UPS where everything is a single unit. So we have a single rectifier, a single inverter, a single bypass. So there's no duplication. But then we have what we call true modular, where everything is replicated. So we have effectively multiple UPSs parallel together. So everything is duplicated. So every module has a rectifier, inverter, a bypass, control, and display. And then we have something in the middle, which we refer to as semi-modular, because you can have like modules of rectifier inverters, but then you might have a common bypass and a common control as a thing. And there's pros and cons to everything. It's just a matter of getting the right thing in the right job. And the UPSs are designed to protect against different types of power disturbance. So if you just wanted to protect against mains fails, snags and surges, and have a little bit of break, we'll have this offline UPS, like a single conversion UPS. If you want to protect against that and under and over voltages, we'll have a line interactive VI. And if you want to protect against all disturbances, including frequency variation, harmonic distortions, transients, then we need a class 1 online double conversion UPS or a VFI. Now, a true online double conversion UPS will always have a VFI, which is the voltage and frequency is completely independent to the input. The output waveform is sinusoidal at all times, and the output dynamic performance is 111, which means there's no break at all for any period of time. And this is in accordance with 62040 Part 3, which is the standard for UPS performance. Now, HTM does talk a lot about dual supplies and dual sources, and it does create some confusion. HTM is a guidance of the various ways of providing a UPS support in a healthcare environment. And it's important to understand what we're going to need as these dual sources and where these dual sources are. Now, in HTM, it says the rectifier and bypass of the UPS may have a common supply connection, so a single feed. The ideal connection should provide separate connections for the rectifier and bypass line. Now, what that means is we want to have the rectifier in feeding the rectifier, and we might, on a single supply, we'll have that same supply feeding the bypass. If we have dual supplies, we split them and feed them separately. Now, it recommends that rectifier and bypass are fed separately, but not necessarily from a different PES. If you have a central UPS, and we'll talk about that different line, it doesn't necessarily need to have dual supplies. And just a note here that many modular UPSs will split the supply and protect each one for the rectifier and bypass internally within there. So if we do have a problem with a rectifier, it doesn't take out the whole supply, we still leave the bypass available. Now, one thing to note is if we have dual supplies in, the UPS doesn't choose which one to use. It will always use the rectifier supply when it's available, and if that supply isn't available, it will actually transfer to battery and run on battery until that's exhausted before transferring to the bypass. Many people think that it will choose which supply, and it doesn't. Okay, bypass is always a backup. Okay. Now, it says that we can enhance the infrastructure resilience by adding a UPS, and a single conversion UPS may be connected to the dedicated final circuits. Okay, so this is the example from there, and it shows dual source supplies using a local UPS. Difficult to see, it's in HTM, but the UPS is here, fed from 2 different sources. Okay, so that's the dual source, and that's feeding directly out onto the medical IPS and to the load. Okay, so we haven't got the dual source is coming into the UPS IPS, not at the final circuits. Okay, so this is a final circuit UPS. Now it also says we can make additions by having an auto changeover supply to the secondary power source and or manual changeover. So this suggests that an ATS, an automatic transfer switch, can change over to the SPS from the PES and may be provided to the input UPS. Now it could also be at the final circuits. So this is an example again from HTM, and it suggests that we have central UPS. So the UPSs are here and here. Okay, and the supplies from these is coming to the medical IT, where the ATS is changing over at that final circuit. Okay, the actual central UPSs here and here have one supply coming in. So the dual supply is done at the final circuit. So that's close to the final circuits is reasonably practical. Okay, so if there's any problem with the UPS or the distribution, it can change over automatically at the medical IT systems, the IPS. So in the final circuits chapter, it talks about, shows an example of a UPS at the final circuit. So we have a UPS here with a medical IT. It doesn't specifically say where the ATS is, so it could be before the UPS or after the UPS, but we have a form of transferring between the 2 sources, PS and SPS, feeding through the UPS, feeding through the medical OT to the final circuits. So what we're seeing is that the dual supply, the dual sources, should be as close to the final circuits as possible. So if we have a UPS feeding the final medical IT system to the final circuits, then we would have the dual source coming into that. If we've got central UPSs, they have a single input, and that they become the dual source to the final medical IT system. And we do have different people looking at feeding it from both places. So we have central UPS with dual sources, and then dual sources at the medical IT. Not necessarily required. So then we talk about isolations transformers, and this can be confusing of why we're going to use them. So we're going to have a need for isolation transformers, and there's 2 needs for isolation transformers. One is for having dual source supplies, and then one is for galvanic isolation of the output. Okay, and this is not always fully understood. So we have is, again, in the chapter we previously looked at in HTM, it says where for resilience purposes UPS units are fed from different PES transformers, different supply sources, the UPS may experience neutral reference problems, and talk to the manufacturer. So it recognizes that modern UPSs, modern transformerless UPSs, have 4 wire connections to the rectifier and bypass. And this means there's a common neutral connection in the UPS. Okay, so to prevent this, we may need an isolation transformer between the 2 sources, okay, with this type of UPS. So what that means, we look at the difference between a transformer-based and transformerless UPSs. Now, traditional older design transformer-based would have a 3-wire rectifier and a 4-wire bypass where the neutral is going round. Okay, so there is no neutral to the rectifier. Now, on a transformerless UPS, a modern UPS, we have a 4-wire bypass, a 4-wire rectifier and a 4-wire bypass, and the neutral is connected from both inputs together within the UPS. Okay, so if we want to feed that from different supply transformers, different PES, then with a transformer-based unit, it's fine. Okay, we have the neutrals coming in from this transformer, but this is only using the 3-wire onto the rectifier. Okay, because the transformer in there creates the isolation between the two sources. Okay, so when we have a transformerless UPS, because the neutral is connected internally, we need to isolate those neutrals, and we put in a galvanic isolation on one source, typically the bypass, and this will isolate the two neutrals. So this neutral is connected to this neutral, not to earth. So it doesn't create an output galvanic isolation. This is to isolate the two supplies. Okay. To repeat, this is because modern transformerless UPSs have that link neutral. We have to be very careful that we don't link the neutrals of the supply transformers in the building. Okay. So that's one application of an isolation transformer. Now, the other application is for 4-pole changeover. And HTM talks about this. It says where a changeover arrangement utilizes 4-pole devices from primary source to the secondary source, the neutral earth reference will be lost for that period. That actual changeover takes place. So it talks about unstable output and unbalanced load being worse. Now, it does recognize that we need to address this problem. It recommends the use of a 0 phase shift transformer, but it should be noticed that the UPS output would not be unstable because it's lost the input neutral earth reference. The output from the UPS will remain stable, 230 volts line to neutral, 400 volts line to line, but the neutral and earth are not connected, and this is a problem we're trying to overcome. It talks about the 0 phase shift transformer. Now, you need a transformer and you need a 0 phase shift if you want to bypass the transformer. Okay, typically an isolation transformer will have a 30-degree phase shift, so you can't do a make before break bypass on that. Okay, when we're talking about floating neutrals, we are talking about 2 different types of floating neutrals. Okay, and this what does confuse some people, because on a healthy system, the neutral is connected all the way through to the transformer and to earth. Okay, so line to neutral 230, line to line 400. Now, people get confused with a floating neutral when its distribution neutral is lost. Now, this is obviously very dangerous, very unstable. Okay, line to neutral voltages can be 0 to 400 volts, causing a lot of damage. Now, this isn't what we're trying to overcome. This is just to show you the difference between the neutral and earth. Okay, so we have the problem that if we're going between 2 sources, between mains and generator typically, or it can be between 2 main supplies, okay, we have a 4-pole changeover. We're required to use 4-pole changeover for various reasons. Okay, and this is what links the neutral to earth. Okay, so it talks about in HCM the isolation transformer required can be located at a number of points with the UPS system. Be an input to the UPS, the whole thing on the single supply, input supply to the static bypass, or the output. Now, it does guide us in the fact that the optimum option is on the output, on option C. Okay, so we need to understand now what we're doing with this isolation transformer, and how we can incorporate it into our systems. Now, again, there's a lot of confusion between transformer-based and transformerless UPSs, because people think that because there's a transformer in the traditional UPSs, that it creates galvanic isolation on the load. It doesn't. It creates isolation between the sources, not the output. And you can see in this diagram that the output transformer has the neutral directly connected to the input. There's no neutral earth connection inside the UPS. We can't connect it to earth because it's the same neutral as used for the bypass line. Okay, so it's not a case of just putting a neutral earth link inside the UPS. All right, so often confused, but with a transformer-based or a transformerless UPS, we have to add a output isolation transformer. Okay, so on a transformer-based UPS, this is how we look. So we've got a single supply in through the rectifier. It's got that transformer inside, but it's not creating the neutral earth. Okay, so we put another isolation transformer on the output as recommended, and we re-earth the neutral to the load at this point. Okay, so whatever happens on this supply, if we lose the line and the neutral is connected. And this is exactly the same on a transformerless UPS to what we want to do. So we have the single source feed, neutrals connected inside, but we're going to just take 3 wire into the isolation transformer to achieve that galvanic isolation, having the neutral earth there. Now in both cases, that isolation transformer is always on load, and it must be rated for the UPS output to be correct. Now, we've seen there's 2 different types of use for isolation transformer, for dual source and for output galvanic isolation. So if we need to do both, what we would be looking at is on a transformer-based UPS, we have the supply from 2 different transformers. We have a rectifier using 3 wire, bypass using 4 wire. However, we need to galvanic isolate the output, so we add a transformer in there. Okay, just using 3 wire in. All right. Now with a non-transformerless UPS, we've got the dual supplies, so we have to isolate those 2 supply neutrals. So this isolation transformer is connected to the neutral, okay, through the UPS. It's not connected to earth. And then to create the galvanic isolation, we have the output transformer, okay. Now that creates the new neutral earth. Now that means we have to have 2 transformers. We have a non-transformerless UPSs, but we have the option of using an automatic transfer switch, okay, for dual source. Now this is a good alternative to having dual source into the UPS, because it means that whichever supply is available will feed both the rectifier and bypass. So if one, typically we will be running on, let's say, supply 1, feeding rectifier and bypass. Now if that was to fail, the ATS would change it over to the second source, so the UPS would continue to run on the mains, because if you have a dual source, as we said before, if you lose the supply to the rectifier, it doesn't change over inside the UPS, it will just run on battery until that supply is exhausted. Okay, and then we have the isolation transformer on the output as before. Okay, so hope that clears it up. 2 different uses of isolation transformer. We just have to understand what we want when we talk about galvanic isolation. So we move on to a subject that we have a lot of discussions around, is fault clearance on UPS for life safety. Healthcare is obviously life safety. So we have a quick poll here. Be interesting to know what you say, because we have different views and we want to understand what we're looking at. Okay, so we got, if you can get the opportunity to add your answer in, and then we discuss how the UPS does react to downstream faults, and hopefully this will help. So thank you. There's a lot of people voting, and we'll leave it open for a little bit longer. I will share the results with you in a moment. And we've got a good number on and a good number voting, so it's, thank you all for paying attention. So, okay, voting has slowed down, so I'll close that and we'll share that. Okay, so we see that 64% look at the running load, 36% look at the fault current. Okay, so we'll have a look now at how a UPS operates and maybe what we should be considering. Okay, so what we're looking at is a UPS running online, typically double conversion UPS running online, and we have an output short circuit. And now the UPS will operate in different manners, has different capabilities. The inverter, being made up of transistors, has a very limited fault clearance, and it's typically said in sort of in IN, quantities of IN. So 2.5 IN for 100 milliseconds is an example. It could be 3 IN for 40 milliseconds, but it's limited. As compared with the bypass supply, which has very high fault clearance because we're using the mains. So maybe up 10 IN for 10, 20 milliseconds. Now UPS goes through a number of sort of decision making. So first of all, it says, is the downstream fault greater than 150%? Because most UPSs can run 150% as an overload. Over 150%, it treats it as a short circuit. So if it's under 150%, it will time. Okay, it's an exponential timer, so it can run up to 150% for maybe 30 seconds to a minute, 125% for 10 minutes. It'll try and clear the fault. If it does, returns back to normal operation. If it sees it as a short circuit or it times out, its first thing it says is the bypass available, because if it is, I'll transfer the load to the bypass because it's much higher capability and try and clear it using that. Okay, it transfers in about 3 or 4 milliseconds, tries to clear the fault. If it does, it returns the load back to inverter, leaves an alarm up saying there's been a short circuit. If it doesn't clear it, something's got a trip. Okay, so it's either fuses in the bypass or the upstream. Now, if there is no bypass available, because we're on a mains failure, the inverter will go into short circuit, and this means it will current limit, reduce the voltage, and give as maximum current as it can to try and clear that fault. Okay, if it doesn't clear the fault, it means the inverter will turn off and we drop all load connected. Now, when we look at 7671 in safety services, it says when you use a UPS, it should be able to operate distribution circuit protected devices and be able to start safety devices on inverter, on battery. Okay, so HTM also refers to this. It talks about the UPS protective devices should be capable of clearing downstream circuit protection in similar to other distribution boards and in accordance with BS 7671. So what we're trying to achieve here is, if we've got the UPS, we'll be feeding typically through a sub-main onto different protective circuits. Okay, and we want, if any final circuit has a problem, any one of these circuits has a problem, the protective device must operate. Okay, it must operate so we can keep the rest of the life safety systems working. One thing to note is if we have a fault here, do we operate that protective device? Because if there's fault here, we've lost everything anyway. All right, now that might be different if we've got two different things connected. Okay, so if we have a fault here on the non-life safety load, that to operate, because we want to maintain the life safety loads. Okay, if we have all life safety loads and we have a fault here or here, or if we have a fault here, we want one of these to clear. If we have a fault here, we need this to clear. Now that becomes quite difficult to get that discrimination between it. Okay, so we're looking to have the fault current and use the size of the UPS to operate those protective devices. Okay, so when we look at our flow chart, okay, we've now got to the point, we've seen a short circuit, but we've got to consider that we cannot use the bypass. We'll use it if it's available, but obviously the UPS is there in case of a mains failure, and if the mains is not available, we cannot use bypass. So therefore, we have to use the inverter to clear the downstream fault. Okay, if we don't clear that downstream protection, it's not compliant. Okay, so what that means is that if we have a short circuit on the output of the UPS, the inverter must be able to operate protective devices in the required time, okay, on inverter while on battery, and it must be able to start up any connected load. So in some cases, if a UPS is used for a life safety system, it might be connected with motors which have a high startup current, okay, so it must be able to handle those as well. So we're actually sizing the UPS in most cases to be able to handle the fault currents rather than the running load of the system. Okay, so quite often we're increasing the size of the UPS inverter to operate those protective devices because we have that limited current available on the inverter, and this can increase the cost of the UPS quite significantly to make sure we get a big enough inverter to operate those devices. Okay, we want to make sure though, rather than have just putting a massive UPS in, which we'd be happy to supply, but there is alternatives, is to make sure you use the smallest, fastest protective device you can in any circuit, so we can better match the UPS to the load rather than just the fault currents. Okay, it's very important that you take this into account. Okay, speak to the manufacturers. We've done extensive testing on our UPS inverters with circuit breakers to make sure that we are tripping them when required. Okay, so moving on to batteries and healthcare. A lot of talk about batteries here. They talk about VRLA being the optimum battery with a 10-year life. It says no toxic gas is emitted from the battery and no special venting requirements. Now, we do get hydrogen from batteries, and if you look at safety data sheets, it says never place them in sealed or gas tight enclosures, because in normal operation there is a small amount of hydrogen, not a lot, but we cannot put them in a sealed room, and we have to make sure that we have some ventilation. Okay, it recommends that they're 10-year, although batteries come in 5-year, 7-year, 10-year, 12-year. It sort of recommends us having a good long life battery as opposed to a 5-year battery. That's good value for money. It shouldn't have push on terminals, okay, often put in small UPSs, and if not, we have to add cost by putting in a threaded terminal, and also it should be flame retardant as well. Okay, so when we look at battery life and environment, it recognizes in HTM that batteries age very prematurely due to hot temperatures. Okay, so ideally we should be looking at 20 degrees. A battery will operate in various temperatures, but over 20 degrees it starts to degrade the battery quite significantly. It's often overlooked, but we can see here the hotter the temperature, the sooner the battery will age, okay, and fail prematurely. Okay, so ideally we need to keep that at 20 degrees for maximum life out of the battery. So when we're putting a battery in, HTM talks about having split banks of several strings to allow redundancy in servicing. It says battery cell or string monitoring should be considered where appropriate. And obviously having this option of having a split battery to be able to maintain it and fix it without actually taking off the whole battery in one. So we're looking at parallel strings of batteries. So if one battery was to fail, we've still got the other battery in line. But if we want to be able to maintain it, that has to be physically put in, arranged where it's safe to work on one battery string at a time and isolate the one string at a time as necessary. When it talks about considering battery monitoring, personally, we think this is a very good thing. Battery monitoring will always look at the battery and give us a state of the battery, if it's good or bad, okay? Which will alarm out and tell us if there's a problem with that battery that we should be looking at. It monitors volts, impedance, temperature, current on discharge. But we also do management systems that will extend the life of the battery when kept at optimal temperatures, because it balance charges the system. Something that we put in a lot of data centers nowadays, and very critical areas as well. So it talks about battery autonomy on single conversion UPSs, and we see this in healthcare and other life safety. People are looking at, oh, we just put a UPS in, we put in a small single phase, but they're typically not there for healthcare applications, but can be used for computer systems with short autonomies, because typically these will have a single input, no manual bypass. Internal batteries don't meet the requirements of the terminals and things like that. So typically not used for actual healthcare, the grade A sites, but for sort of like small computers for a small period of time. The battery autonomy, it talks about 1 hour or 3 hour, depending if you've got an SPS. So typically in a UPS situation with a medical IT system on it, we look for an hour battery, because you'll have a secondary source from a generator or an M+N UPS available within 15 seconds. One thing HTM doesn't consider is the end of life of the battery, okay? So battery will lose capacity over its life. So ideally, we should have the hour battery at end of life, okay? So that means we would have to typically oversize the battery at the beginning. The manufacturers won't put that in unless you specify that you want that, okay? Once you've sized the battery for your hour, it recommends that we should prove it, that it does what we say it's going to do. So, if you've got a 50 kilowatt UPS for an hour, prove it, okay? So what we would need to do is actually put a load bank on, discharge the battery for the required time, and prove it lasts the autonomy required, 1 hour, 3 hours. Now this is an option, and we will do this once we've got the UPS up and running, charging the battery. We'll come back after it's charged the battery, typically a week later, and discharge it, okay? So we've seen the UPS and battery, there's different needs. The UPS has a wide operating temperature. It's got airflow, needs airflow, very sensitive to dust in the environment. It weighs hundreds of kilos, typically placed in similar equipment, where the battery needs a much more stable performance in the environment, in temperature. There's a small amount of hydrogen that should be considered, and the access and containment around that battery should be considered of who's got access to make it safe. Okay, it's often best to put a large battery in a dedicated room, or we could simply partition it off, making sure the environment's right temperature to make it safe. Okay, so when we look at the considerations, we've talked about a lot very quickly, I appreciate that. There is a lot to talk about. We have got some typical design considerations. Typically, what's the type of load that we're going to run in that healthcare situation? That will determine the output quality of the UPS. We need to understand the difference between kilowatts and kVA. Okay, not all UPSs are at 1 power factor. Okay, we need to understand if we're putting the UPS as a central UPS with a single source or a final circuit with the dual supply. Okay, with that supply requirements, again, where we're going to have dual and single sources, where's that required in the system? Okay, redundancy of UPS. So especially if you've got UPS at final circuits, we might want to consider adding an N+1 UPS to give us redundancy in the UPS, or if we've got centralized UPSs at N+N. Autonomy must be done correctly, obviously to the regulations. You might want to consider end of life as well, because of most life safety systems, we would do it for end of life. Redundancy of the battery does talk about having secondary strings or parallel strings. This is for maintenance, redundancy, and if we monitor and manage it, we can actually make that battery very, very resilient system. Make sure we design the system for installation and maintenance. This is not always done. Many UPSs are stuck in a cupboard with no fault for the ongoing maintenance. The UPS will last 10 to 15 years in good environment, but we must be able to get to it to maintain it. Okay, the size and weight of the UPS makes a big difference when we're looking at the installation, especially the batteries can be extremely heavy. And then we got to make sure that that location is safe for everybody and the environment is correct. HTM does talk about monitoring the UPS. Okay, so we must know that the UPS is online available. It's surprising how many people just don't even check the UPS is there. Okay, so a lot of this comes down to specification. Okay, we need to specify exactly what we want. Specify the load, the power factor, the output, redundancy, efficiency, very important nowadays with sustainability, modular, decentralized, manual bypass, software and remote monitoring, very specifics on around the battery. Okay, making sure that we get exactly what we want with a very good high quality system that matches our lead, rather than a poor spec that will give us a poor solution, not exactly what we was planning. Okay, so I've gone through a lot of that very quickly because there is a lot to talk about with UPSs, and I can see that we've had a lot of questions in, and I'll hand back to John now so he can ask me those questions.
Hi, thank you very much, Alex, for a very interesting and in-depth presentation. Very interesting, and obviously power resilience for hospitals and healthcare facilities is absolutely critical. I'll run through one or two of the questions we've had, if I may. One attendee has asked, do cooler temperatures reduce the battery efficiency the same way that hotter temperatures do?
Okay, temperature, like I say, is very critical on batteries. We size batteries at 20 degrees because that's what we say you should run them at for maximum life. And if we size it at 20 degrees and then say you run it at 5 degrees, it won't extend the life, but it will shorten the autonomy. Okay. Conversely, if we have a hot room, 30 degrees, the performance of the battery is better, but we will halve the life of the battery. Okay, so it is very critical. Temperature is very critical to the life and performance of the battery. Yeah.
Thank you. Another attendee's asked, what are the primary differences between uninterruptible power supply and isolated power supply in the context of medical environments?
Okay, so the UPS, the uninterruptible power supply, is there to back up the critical load when the mains has a disturbance, either an outage, frequency disturbance, or a surge or a spike. Whereas a medical IT system, the IPS, is there to isolate the load from a neutral earth. We're actually getting rid of the neutral earth on their load, and we use an IPS system to do that. That's so we have, if we have a fault on the output of the IPS, we don't go tripping all the breakers we get an alarm up to say there's a problem. Everything will continue to run. Only on the second fault will we lose the protection. So completely different things, often put together. Often the UPS is feeding the IPS system.
That all makes sense. Thank you. That's very clear. Somebody else has asked, in accordance with the HTM 0601, what minimum hours of UPS battery backup are required in case of the main electricity? Sorry, in the case mains electricity is absent for each piece of health and safety equipment. So the minimum hours of UPS battery backup required if mains electricity is absent for each piece of health and safety equipment.
Yeah. Well, if HTM talks about having the SPS available within 15 seconds and gives us an hour requirement. If that SPS isn't available, then it's 3 hours. But we're talking about, if you're talking about safety systems as well, there are obviously other regulations for life safety systems that might require longer for that. But typically for the healthcare HTM guidance, it's 1 hour or 3 hours.
Thank you. Another attendee's asked, said mostly UPS batteries are provided within the UPS. Are there any specific requirements for those?
Yes, and this is where a lot of people would just specify a battery, UPS without taking into account those batteries. If we have, typically small UPSs will have internal batteries, and they can quite often be a 5-year battery with push-on terminals and not flame retardant. So the battery, sometimes we have to put an external battery on a small UPS purely to get the right type of battery for that system. So the ones with threaded terminals for 10-year battery with flame retardant. So yeah, just asking for a 50 kilowatt UPS with an internal battery isn't good enough. It's about specifying exactly what you're going to use it for and what you need. Definitely.
Thank you for answering that one. Another question, what is the percentage energy loss through double conversion?
Okay, that does vary on by manufacturer to manufacturer. Now, very old systems would be 90% or less. Over the years, we've greatly increased the efficiency of UPSs, and with the very modern UPSs, we're looking at over 97% efficient online in VFI mode. Yeah.
Another attendee has said, within the documentation to be considered, you didn't mention CIBSE LG2 Healthcare, which requires standby lighting grade A to be UPS and generator supported.
Agreed. We was looking at specifically through the HTM. Yes, that is a consideration, and that is for a different life safety application rather than HTM. And there is a lot of discussions around what level of backup you require for that lighting with that. And that might be a case of putting in a central emergency lighting system and running off a different system to the UPS. It does, there is a lot of talk about this because of things have changed, and there's different levels of emergency and backup required for the lighting. So yeah, that's a lot of careful planning on that is needed for sure.
Thank you. A safety related question, and one that I know has been raised around lithium batteries quite regularly. One attendee has asked, have you any thoughts on lithium batteries and fire risk or fire issues?
Yes, that is obviously a concern for everyone. Now, what I would say in healthcare applications where we're looking at a 1 hour or 3 hour battery, the advantages of lithium are kind of taken away, because the advantage of lithium is the efficiency at very short, fast discharges. When it comes to 1 hour, 3 hour batteries, the benefits of lithium are reduced, and typically due to that cost of the lithium and the fact that guidance talks about having, the VRLA batteries, we're not seeing lithiums being put in hospitals. Now, we do put lithium batteries in other applications, especially when it's a short, fast discharge. And yeah, we need to consider that it's in a proper room that's rated for the fire rating typically. Yeah, there are new guidance around installing lithium, but it's not something that we're seeing being used in hospitals at the moment.
Thank you. I should point out to all attendees that we have had a lot of questions, and any that Alex isn't able to answer online on this occasion will be forwarded to Alex and the company, and they'll do their best to get back to the asker of the question. This may be one of them. One attendee said, "Thank you for the informative presentation. Could you provide some practical examples or case studies that demonstrate the successful implementation of AI technologies with Kohler used in UPS and IPS systems with medical environments?" I don't know whether that's something you need to get back to the person who's asked the question on separately.
Yeah, probably. We're not seeing a lot of AI being used in healthcare. I mean, we are seeing AI coming around with UPSs in general to look at the maintenance requirements and life expectancies of the UPSs, not generally so in the healthcare application.
Thank you. A lot of questions coming in. Another one is, what is the maximum recharging rate of a system after use, and do hospitals increase supply capacity to cover recharging?
Okay. Again, very manufacturer specific, and also depending on the autonomy of the battery. So UPS will have a charge capability, and with a VRLA battery, we will typically charge it at C10. So if it's a 100 amp hour battery, we charge it at 10 amps. So we're actually limiting the supply to the unit. So we're not taking the maximum supply that we can from the input. So we actually control the amount of current going into the battery so as not to overload the supply. The manufacturers will give the full load input current for the UPS on load and on recharge. So the input supply will have to be larger than the requirement of the load for the battery recharge, but it's not unlimited. It is limited on the charge current.
Thanks, Alex. Another attendee's asked, what's the need for a static bypass where the UPS has to operate downstream devices under BS 7671?
Okay. For a life safety system, we're looking at BS 7671 under safety services, and it says it must be able to operate on inverter on battery, so not using the bypass. In non-life safety systems, we can use the bypass to clear the downstream protection, but not for life safety systems.
Thank you. Another question is, would you recommend a battery cabinet sitting on a metal checker plate floor with no insulation?
I don't see a problem. All battery cabinets and frames must be earthed in accordance to the regulations for stationary batteries. So we are going to have the cabinet and the floor will obviously be earthed. Working on batteries can be dangerous, and we do have to make sure that we only have, competent, trained people working on batteries. We see far too many accidents because people don't treat the battery with the respect it requires. So yeah, I mean, the frame, the battery cabinet is all earthed. I would imagine there'd be more of an issue if it wasn't on a checkered plate. I think what we have to be careful with checkered plates is, just the safety around making sure you don't drop anything through it.
Thank you. Quite a detailed one here. Regarding the isolation transformers, one of the attendees said, we've recently refurbished all catheter labs with UPS connected to C-arm X-ray scanner. Instead of installing multiple isolation transformers, we're looking at installing a paralleling neutral contactor at section board level. Section board is dual TX supplied. The theory is that the paralleling neutral contactor will be designed in such a way that a neutral connection will be maintained and made before any planned or unplanned switching at section board level. I'd be interested to know your thoughts on this arrangement. So quite a detailed question.
Yeah, we see there are various ways to protect against the loss of neutral earth. Now, having that neutral earth contactor on the supply changeover, has to be very controlled, typically PLC, and that is a good solution of maintaining the neutral earth in all cases. You do have to consider if it's worth it in the right application, because if we've got a 1 MVA supply, let's say, and the UPS is only a 50 kVA, it might be better to have an isolation transformer rather than having that whole changeover on that neutral earth contactor on the supply. Also, if we have an isolation transformer more low, there's less chance of having a 4-pole breaker down, upstream from the UPS tripping and causing a problem. So very application specific, but we do see the use of neutral earth contactors a lot, especially around the data center market. Yeah.
Thank you. Another question, in the galvanic isolation slides you showed options for either an extra isolation transformer or an ATS. What are the benefits of using an ATS? Is it cheaper?
Yeah, it does depend on the size application. It can be cheaper. Benefits of ATS to the dual supplies, it means that it will choose the supplies available. Now, this is where do get a lot of confusion, that people think if you've got dual supply into the UPS and you lose the rectifier supply, the main supply feeding the rectifier, that the UPS will then swap over and use the secondary source to feed it, but it doesn't. So having that ATS, the UPS will remain on mains and have that battery as a backup in case both fail. So yeah, everyone has to analyze and risk assess what they have, but we see that the use of ATS is a very useful way of maintaining the supply to the unit without having to use the battery if not necessary.
Thanks, Alex. Given the in-depth nature of the presentation, we're getting some very good technical questions. Another attendee has asked, is it better to have smaller downstream protection devices or a bigger UPS to handle faults? Doesn't the extra wiring and distribution cost of smaller devices make it a more expensive option?
It can do, for sure. The smaller the devices, the smaller the inverter. So it does depend. In some cases, you will only be able to have, one size of the smallest you might have, maybe a 32 amp. And in that case, you will need a bigger UPS. And it's significantly, a significant step up to the requirements of the load. So in these cases, when you're putting in a big UPS, it could be cheaper to have local smaller supplies, but multiples of them. Very, very site specific with that and how it's done, because if you've got a central UPS, it might be so big that you can have the larger breakers anyway. Yeah.
Thank you. I'm sure this one will be of a wide-ranging interest. An attendee has asked, are there any restrictions on using lithium-ion battery systems in hospital buildings?
Sorry, repeat that?
Yeah, the question, Alex, was, are there any restrictions on using lithium-ion battery systems in hospital buildings?
I'll be honest, I don't know of any restrictions. But like mentioned earlier, if it's for, typically we're seeing VRLA is just the cheapest option. That's around those autonomies of 1 hour, 3 hour. There is a new regulation that I am not, to be honest, up to date on, that came out at the end of last year on installation stationary lithium batteries. Like I said, it's one of those things that we're not seeing used in healthcare, but I'm sure at some point we probably will.
Thank you. Somebody else has asked, if I have a generator, can I reduce the UPS battery size?
Yeah, quite often you can, depending on, as always, sorry about this, but it depends on application. But we often see if we have a large UPS on a generator, people are sizing the generators for a traditional way of sizing a generator to have a 60% load step. Modern generators can't have that 60% load step. They're designed to be small load steps on modern efficient generators. The UPS will allow us to step that load in gradually onto the generator, meaning that if you size it correctly, we can have a smaller generator because we have the UPS taking the step load off of it. So yes.
Thank you. Somebody else has asked, how often does a hospital UPS need servicing, and concisely what's actually involved when that occurs?
Okay, the UPS, according to the guidelines and from us, to be honest, is we like to maintain the UPS twice a year. It should, however, be checked on as often as possible. I think HTM says minimum monthly to make sure that it's available. But on a maintenance, the prime function of the UPS of the maintenance is to make sure the UPS is available when you need it. So we're going to check that the UPS is A, online, B, available to work, that the batteries are healthy and will be there if called upon, that the calibration is correct, and everything functions as needed. We'll also make sure that the consumables like the bats, caps, fans are recommended if required. So very, very critical to have maintenance on the UPS by someone who actually knows what they're doing. Yeah.
Thank you. Just looking ahead, another attendee's asked, do you see fuel cells replacing batteries and generators for UPS in the future?
Yeah, there's a lot of work around fuel cells and large batteries to back up for generators. At the moment, it's not there, but obviously there is a lot of work around hydrogen. But there's a lot of problems to overcome with production of green hydrogen, with storage of hydrogen, and it's not necessarily going to be a good thing for backup. It might be a case for sort of like grid support and things like that, yes, but we don't see the end of generators anytime soon using, you know, fuel. Nowadays we can use HVO, which is good, and you know, we can top up HVO. You can top up fuel on the go. So if you had a very long extended outage where you can't top up necessarily a battery to do that, so it's something that will come, but not in the immediate future.
And I think probably the last question, because obviously we have time limitations, an attendee has asked on a practical level, have said, we have recently had Delta zigzag transformers installed on the input side to dual supply transformerless UPS systems for medical IT in theatres. What are your thoughts on these being used? We've never had these before.
Yes, we need isolation. It's on the input, and it's because of the dual sources from two different transformers. Then you're going to need some sort of isolation to isolate between the two neutrals of the supplies, and you will need for HTM to galvanic isolate. So it is a solution to have a transformer on the bypass and rectifier, connect the neutrals together, connect it to earth, will overcome the problems of the dual source and the galvanic isolation. So yes, it is something that is a reasonable, practical way of achieving what we require. Yeah.
Thank you very much, Alex. I think we're out of time now, but as mentioned before, any questions that attendees have put to COLA will be answered by the company subsequently, and audio and video recordings of the webinar will also be available. Thank you very much, Alex Ems from COLA Uninterruptible Power, for a very interesting and in-depth presentation. And thank you all attendees for attending, and I hope you found it useful and informative. Goodbye. Thank you.
Yeah, thanks for having me. Goodbye.